Hello everyone, my name is Gyanendra Singh and today I'll be presenting my capstone project on bike sharing demand prediction, which is a supervised machine learning project in which we'll be using different regression algorithms to seek out some insights from the given data. So first let's start with the problem description first and so currently, rental bikes are introduced in many urban cities for the enhancement of mobility comfort, and it is important to make the rental bikes available and accessible to the public at the right time as it lessens the waiting time and eventually providing the city with a stable supply of rental bikes becomes a major concern. A crucial part is that the prediction of bike count required at each hour for the stable supply of the rental bikes. So, uh, going forward with our data description, so we have a data set which contains attributes information like date, rented by count, our temperature, humidity, wind speed, visibility, dew point temperature, solar radiation, rainfall, snowfall, seasons, and in seasons we have winter, spring, summer, and autumn, and holiday, whether there was a holiday or there was no holiday on any day, any given day. And next one will be the functional day, in which we will be getting a functional day or a non-functional day. So we'll start with importing our libraries. So we'll be importing some important libraries like pandas, numpy, matplotlib, and seaborn. Next one would be to read the data. What we'll do, first of all, we'll mount the drive, and after that we'll provide a path for the data set that has been given to us, and then we'll read that data using pd.read csv and store it in a new data set, in a data set called named bike underscore df. So we'll start with the data exploration and data cleaning. So we can see here the head of the data, or the first five observations in the data set. We can also see all the column names here, right? Next one is the tail of the data set, or the last five data observations in our data set. Next would be checking the number of columns and the number of rows. So the number of rows came out to be 8,760, and the total number of columns came out to be 40. Now we'll be checking the information, all the information regarding the data set, info of the data set. So here we can see there are 14 columns over here, and these are all the data types of all the columns. And here we can see there is no null value in any column, so which is a plus for us. And so again, if we talk about the observations of the data as it is, so there are no null values or missing values. Next one is the date column. Actually, we need to convert it into a proper date type. Okay, so here it is an object type, we will be converting into a date type. Next is the columns which need to be converted into a numerical types. So actually the seasons, holiday, and functioning day are categorical variables over here. So what we will do, are categorical, so we'll convert it into a numerical type for easy rendering of the data, so that we can use that data in our algorithms, and we can use that data to seek out some insights from the data. So for example, for a holiday, we have two categories, holiday or no holiday. So holiday we can give 1, and for no holiday we can give 0 as the numerical value. Next is, we'll rename some columns also because they contain some blank spaces and some special characters which will, kind of hinder us to write that data, variable names actually. So as we can see here, all the column names over here. Next one is, we will be renaming all those columns to much more not appropriate but easy names, easy to write names. So we've renamed all those columns. Next one is, we have converted the data type of date column to a date type column, a date type data type, in which it will be giving from which we can extract actually the month, day and the year from the database, from the date actually. So here we will be creating two new columns, and from which we can get out the day name and the date and the month of that given date. So by using that day name, we will create a new column. Using that day name column, we'll create a new column which is weekdays or weekends. We will seek out whether it is a weekday or a weekend. So 0 is weekdays and 1 is weekends. So here we can see, right? 0 we will be using for weekend and 1 for weekdays. Next one will be, now we don't have any use of this day column and the date column anymore because we've extracted the data from it, and it will actually lighten up our data for faster processing, I would say. Now we will take out the value counts of all the other categorical variables. First one would be the seasons. So here we can see the value counts of all the seasons like spring, summer, autumn and winter. Let me just, yeah. Next one would be the holidays. So for holidays it is 8,328, and for no holidays it's 8,328, and for holidays it is 432. Next one would be the functioning day. So non-functioning days are only 295. Yeah. Next one is the next categorical count we can take out of the months. Yeah, so the months, like all the months, the January, February, so all that counts, like number of times that they are came across in the data set are here. Next one would be the weekends or weekdays. So weekends, as we have discussed earlier also, weekdays we will be representing by 0, and weekends we will represent by 1. Now we'll see the description of the data as kind of summary of the data that we have been given. So here we can see for all the numerical variables, we have their count, their mean, their standard deviation, minimum, all the quartiles, and and the maximum value. Next one, we'll again check, we'll re-verify whether there are any null values or not. So here we can see there is no null values, so which is a plus for us, and which is a plus for us. So we don't need to, we won't have to remove any values for null, which were null values. So here we can in the visualization also we can see there are no null values. Here we can see there is no null values. So moving forward, we'll go ahead with the EDA. So over here what we'll do for all the numerical columns and all the categorical columns, or the categorical column lists, we'll check for the outliers, and for the outlier detection we'll be using box plot with so here we can see Like here we can see we've used a box plot for rented bike count, and these are the whiskers, and this is the box plot. And similarly for all the columns we have got our box plots. And next one would be what we'll do, we'll make a bar chart for all the categorical columns, the categorical columns that we have got, and we will compare it with respect to the target variable. So our target variable is a rented bike count. So here we can see for the categorical variable of holiday, whether in the holiday or non-holiday, what was the count of the rented bike. Next one is the functioning day, whether so here we can clearly see that on a non-functioning day no bikes were rented. Here we can see on the summers the bike rent count is the highest. Here we can see in the month of June the bike rent count was the highest, and it start increasing after the month of March. Yeah. Next one would be in weekends or weekdays. So we can see on weekdays the number of rented bike counts is the highest. So same is written over here in our observations from all the bar charts. So first one is summer season had the highest bike rent count. Next is the bike rental in winter is very less compared to the other seasons, and the high number of bikes were rented on no holiday where when the days where there was no holiday. On no functional day, no bikes were rented, and we have 295 counts of those no functional day. So thus we can drop those 295 values, because the columns we are having only but the column having only yes will not add the value to our to any of our value to our any of our insights. So thus what we'll do, they will not be useful for us. So what we'll do, we'll drop those columns, drop those observations, not columns. Next is the most of the bikes were rented on weekdays, and from March the bike rent count started to increase, and it was highest in the month of June. Okay. Now what we'll do, we'll check the bike rent count using trend lines with respect to the hour on functioning days, weekends or weekdays, seasons, and holiday columns. So all those categorical values basically. So okay, let me just open it up from here actually, or else I'll have to rerun the whole program. Let me see, sorry for the hiccup. Okay, here, yeah, so let's continue from here, from where we have left. So first of all, we will check the bike rental rent according to the hour on holidays and no holiday. So blue trend line is for no holiday, and green trend line is for holidays. So here we can clearly see that there's a peak in demand between 7 a.m. 6 to 7 a.m. we will say to 10 a.m. right? There's a peak in demand between these hours. and because that might be the case because that is the time when everyone goes to their colleges or their offices for their work, actually workplaces. And for no holidays, uh, the case was a little bit different. The bikes which were rented were very less. Next is again, there is a peak from 4 p.m. Here we can see from 4 p.m. to 7 p.m. We have a peak in demand for the bike rents. So that might be the time when they uh, leave from their workplaces for their home. So next one would be bike rented trend according to the hour of the day on functioning and non-functioning day. So here for functioning day, the blue trend line is here, and for the non-functioning day, the green trend line is over here. We can clearly see for the non-functioning day there was no bike rented. Yes. So here there is the trend for functioning day, same as no holiday. Only difference is for no functioning day there is no bike rentals. So if we drop non-functioning day rows, we'll be left with only the functioning day values. Thus our columns will have some same value throughout and will not be helpful. So we will just drop that column all around, right? So we will drop actually this functioning day or non-functioning day column because it won't be that much helpful for us. Next one is according to the hours in seasons. So for each season, like for winter, spring, summer, and autumn, this is the trend line. These are the trend lines. We can clearly see for the winter the bike rentals are the lowest, and for the summers it is the highest. Next one is for different months, right? Yeah, let me just zoom it a little. Yeah. So another one is for weekends and weekdays. So we can clearly see for the weekends the demand is lower if we compare it with the weekdays. So next one would be, next we will move forward with yeah. So next what we'll do, we'll check the distribution of the targeted variables, right? The targeted variable is bike rented count. So as we have seen earlier also, like in the beginning, that there were outliers in the data in bike rented count, which was the target variable. So here we can clearly see the distribution of the target variable. We can clearly see that it is slightly right skewed. So what we'll do, we'll normalize our target variable by using root square method. So after we've adjusted we actually normalized the values, we can clearly see that our dependent variable uh, uh, doesn't have any outliers, and it is like much more evenly distributed, right? We can clearly see the difference from here to here, right? Next, what we'll do, we'll check the distribution of our independent variable. So this was our dependent variable or the target variable. Next one, we'll check the distribution of our independent variables. So here our independent variables are our yeah, okay. So this is our dependent variable only. So we will not be reading this. So the hour is our temperature, humidity, wind speed, visibility, dew point temperature, solar radiation, all the independent variables are over here. Right? So we'll move forward. What we'll do, we'll normalize these values also using using square root method, and after the normalization we can see um, all the distributions are somewhat even, and all the data, most of the data is evenly distributed, right? We've normalized these values also. We'll use those values also only. And now we'll check the relationship between the dependent variable and our dependent variable, which is our rented by count, and the remaining columns, all the rest of the columns. So here we can see, so yeah, rented by count versus rented by count. Next one is for rented by count by counts with respect to hour. Next one is with temperature. Next one is with the humidity, wind speed. Here all the relationships are here there. So what we have observed from these plots. So we'll start with the hour of the day. So we have clearly seen that there is a sudden peak between 6 or 7 p.m. 6 or 7 a.m. to 10 a.m. and the office, because people need to go to their office and workplaces or colleges. And again, there's a peak between 4 p.m. to 7 p.m. That might be the time where when they will be leaving from their workplaces or their colleges. So we can clearly we can say that from morning 7 to 7 p.m. actually we have a good count, like increase in the bike rent count, and it decreases actually from 7 p.m. to 7 a.m. Next one is temperature. So when the temperature falls below 0 degrees Celsius, the bike rent count significantly decreases, because clearly the people do not want to ride the bike in such cold temperature, right? So the favorable temperature for the bike rent, for the favorable temperature, the bike rent count is high. For the humidity also, it is inversely proportional to the bike rent count. When the humidity percent increases, the bike rent decreases, bike rent count decreases. Next is wind speed. So up to 4 meter per second, the bike rent count is actually good in numbers. Next is visibility. So if it is obvious that as the visibility increases, the bike rent count also increases. Next one is dew point temperature. It is same as actually the temperature. So when the dew point temperature goes below 0 degrees Celsius, the bike rent count is less, and it looks like it actually looks like that the dew point temperature and the temperature columns have a strong collinearity. So next is the solar radiation. So the amount of rented bike increases as the solar radiation increases. Next is rainfall or snowfall. We can clearly see people do not ride bike in the rain or the snowfall. So next one, what we'll do, we'll check for the collinearity, correlation actually, between the dependent and the independent variables. So here we can clearly see that there's a high correlation between temperature and the dew point temperature, right? Here we can clearly see which is of 0.91, right? So the temperature and dew point temperature are highly correlated. So as per our regression assumption, there should not be collinearity between independent variables. So and we can see from the heat map that the temperature and dew point temperature are highly correlated. So what we can do, we can drop one of them, and as the correlation between the temperature and our dependent variable bike rent count is high, we can see over here bike rent count and the temperature, right, is 0.54, and for the dew point temperature it is actually low, right, 0.2. So when because the collinearity between Our dependent variable, which is bike rented count, is high with the temperature column, so we will drop the dew point temperature column. Also, we'll drop the date column as it is not useful for us because we have created the month and the weekdays and weekend column already from that. So before starting with the modeling, what we'll do, we will copy this data set to a new data set, which is df. So we'll start with the modeling, and yeah, so here yeah, we've started with the modeling. First of all, we'll see the head of the data set we have copied right now, and next is, yeah, so we have dropped functioning. We have to drop functioning day also, right? I have dropped it further. Okay, let's not. Okay, so what we'll do? First of all, since the temperature and the dew point temperature are correlated with each other, and we've decided to drop one of them, which was dew point temperature. So here we are dropping dew point temperature column, right? And next one is date. I guess we've already dropped, right? Oh, we've already dropped that rate earlier. That's why I was getting a little confused. So we have dropped dew point temperature here. Next one, we will check for multicollinearity, for which we will be uh, taking out the VIF values. VIF value. So here we will be calculating the VIF value for all the columns. Here we can clearly see the VIF values for all the columns. So we'll actually have to adjust the values, because the thing is, when VIF values is greater than 5, we'll have to remove those columns. Actually, higher VIF value, for higher VIF value, we'll have to remove those columns. So we can clearly see that humidity has higher VIF value, which is 6.11, which is greater than 5. So we'll remove that column. So we've dropped that column, and after removing that column, we can see visibility also have the VIF greater than 5, and we will remove that column also. So after removing those two columns, we have a range of VIF values range of 1 to 5. Now what we'll do, okay, so VIF calculation, we have dropped the VIF value over here. So here we have dropped humidity and visibility because they had now we dropped those values because we have decided to drop those columns. So again, we will check the value count for the categorical values, categorical column, which was season over here. Now we'll create a dummy variable which will be seasons, right? And again, we've checked the categorical value of holiday column, counts of categorical value holiday column. So we've labeled the holiday as 1 and no holiday as 0. Okay. So for functioning day, yes, if it was functioning day, we have labeled it 1, and if it was non-functioning day, we have labeled it as 0. So again, we'll be checking after the labeling, right? After the labeling, and we'll check the dummy variables also. So season over here. So yeah, so we've created for season spring, summer, winter, like separately, right? Okay. Next, again we will be checking for null values information. So sorry, the summary of the info of the data before going for modeling. So clearly we can see each column has their intact data type, and there is no null values. So we'll start with linear regression first, and after that we'll be doing lasso regression, ridge regression, and elastic net regression also. And apart from it, we'll be doing decision tree regressor, and we'll use hyper parameter tuning also on that. And after that we will be doing random forest regression also, and we'll use grid search on that also. And after that we'll be using gradient boosting regression, and we'll do grid search also on the gradient boosting regressor. So let's start with the linear regression first. So so basically linear regression is a type of supervised machine learning algorithm that computes the linear relationship between the dependent variable and the dependent variable and one or more independent variables. So we'll start with our linear regression first, and yeah, here we have imported all the train and test split from the for splitting the data over here from sklearn, and after that we will define x variable, the independent variable, or the dependent variable over here. So apart from rented bike count, all are the independent variables. So here we've splitted the data in train and test. Next is we have transformed the data, and here we will train the data and test this data over here, and we'll start with the modeling here. And yes, so we will be getting the regression coefficient for all the columns, right? And yeah, these are the regression coefficients for all the columns given over here. And now we'll check for the regression intercept, which is regression intercept is minus 21.47. okay. Next is we'll check for the regression score for the trained data, and which came out to be 0.61. Now we'll check for the prediction, predictions on the trained data and the predictions on the test data. So here we've the values which are came out to be for the mean absolute error, mean squared error, and root mean squared error are given over here. So what we do, we'll save the trained data and set the results in the data frame over here. Yeah, so here we can see the values for linear regression, the MAE, MSE, and RSME values, and the R square value. So we'll evaluate the test data again. We will evaluate the test data set after the training, and the values of MAE, MSE, and RMSE came out to be 5.8, 58.62, and 7.65 respectively, and R2 score or R square score is 0.61. right? So on testing this data, R2 score is 0.61, which is almost close to the trained data set, training data set, R2 score. So hence we can say that our model is performing good, and there is no overfitting that we have observed, and we need to improve our we would be needed to improve the performance of our model. Okay, So we'll check for the, yeah, so we'll plot the predicted values, y values, and the actual values. We'll plot over here for the predicted and the actual values for the trained data and the test data. Okay, so here is the, so yeah, here we have plotted uh, the predicted and the actual value of the test data. You can see by blue lines the predicted data is there, and the green line represents the actual data. Next one is we will check the homoscedasticity. Sorry, it's hard to pronounce. Homoscedasticity. It's very hard to pronounce actually. So we'll check for the we will check by this uh, um, visualization. We will see by this visualization the plotting of the predicted y values and the residuals, right? And for the test data, we have now we will check like how actually the actual and the predicted data is closer to the regression line. And now we'll be checking the residual distribution, so which is evenly distributed, I guess, right? Yeah. Next, we'll move forward with the lasso regression. Again, for the lasso regression, the alpha value is 0.01, and we have we've got the regression coefficients for all the columns over here for lasso regression. We've splitted the data, and yeah, we have trained the data first over here, and that for the training data set, the R score is 6.1, R2 score is 6.1, RMSE is 7.77, 60.46 is the MSE, and MAE is 5.86, right? So what we'll do, we will put that data on over here on the last DF that we have created for the training results. So we have appended that data in the training results DF which we are creating. So here we can see the comparison between the test training data of linear regression and the lasso regression, right? So MAE is quite similar, I'll say. All the values actually are quite similar, we will say, right? Near to each other, close to each other, sorry. So evaluation, and so now what we'll do, we will use our test data after the training. So here our R2 score for the R2 score or the R square score for that our test data in lasso regression is came out to be 6.17, RMSE, MSE, and MAE values are given over here. So we'll again append this to the test results DF. So here we can see this is also quite similar to the last the linear regression test data, right? Here again we'll plot um, we will plot predicted versus actual values, actual data for the test data. Next again we'll plot a scatter plot to check the homosced homoscedasticity. It's very hard to pronounce. With y predicted and the residuals. Again we'll check, we'll plot a scatter plot to check whether the predicted values actually how much they are closer to the regression line. And lastly we would plot the residual distribution, yeah, which is again evenly distributed. not skewed or anything. Next we'll do the ridge regression. Here also the alpha is 0.01, sorry 0.1, and the next we have found the coefficient regression coefficients uh, for all the values, sorry, all the columns. Next the intercept is minus 21.44. And now again what we'll do, we'll split the data set into train and test data, and next we will find out the r square value, root mean square value on the test data first, sorry, training data first, and we'll append those values in the training result data frame over here, so we can actually get a good look on the data. Yeah. Okay, I think I missed something. No, it's clear. So now next, what we'll do, we'll check for the test data set now, and we can clearly see it is quite similar to the lasso regression and the uh, a linear regression. The values are quite similar to each other actually. Again, the plot between predicted and the actual values, and the residual and the predicted values, and how much the regression line, the predicted values are close to regression line, and the residual distribution which is not skewed. Okay, so what we'll do for now, we'll use grid search on our ridge regression. Okay. Here the estimator is ridge regression. We have imported grid search CV from our scalar model underscore selection. Again, here the alpha is the parameter which balances the amount of emphasis given to minimize the RSS versus minimizing sum of squares and sum of squares of the coefficients. So alpha can actually take various values. So if the alpha is 0, the object becomes same as simple regression actually. Objective becomes same as simple regression. And if alpha is infinite, the coefficients will be 0. And last one is if the alpha value is in between 0 to infinity, the magnitude of the alpha will decide the weightage given to the different parts of the objectives. So again, okay, so the best alpha value came out to be 0.1, and the best negative mean squared value, it came out to be minus 60. Am I missing anything? No. So our best PARAMs were applied to the above ridge model, and the score on ridge is after hyperparameter giving. So next one would be the elastic net. Okay, so elastic net actually is elastic net, we have given the alpha value as 0.01 actually, and the regression sorry, yeah, so regression score on the trained data is 0.60, and the regression score on for the elastic net for the test data is 0.61. So we've splitted the data same as we've done earlier also. We will do it same for our elastic net, and we've found out the values of R square value, MSE, MAE, and RMSE. Now we'll append those values to our training result. Yeah. And now for the test result, we'll again do the same, and yeah. So we'll cross validate actually. For then we'll cross validate it, and so the best alpha value is 0.0001, and the L1 ratio was given was came out to be 0.5, and the best negative mean squared error value is minus 60.7. So what is L1? L1 ratio actually, it is a range between 0 and equal to L1 0 and 1 actually. And if L1 ratio is 1, the penalty would be L1 penalty, and if it is 0, the penalty would be L2 penalty. And if the value of L1 ratio is between 0 and 1, the penalty would be the combination of L1 and L2. Here again we've plotted the predicted values against the actual values and then the residuals and the predicted values chart, scatter plot. Next one is how much the actual and the predicted values are closer to the regression line. Then the residual distribution again. So we saw that in linear regression, lasso regression, and in ridge regression, and also in the elastic regression, we are almost getting the similar R2 scores. Right? So it is in between 0.61 to 0.62, in between that value only. Right? So we'll move forward with this decision tree regressor. Right? And for which we'll split the data into train and test data set, and we'll get out the values for the score for the test data set and train data set. Next one would be we've splitted the data and took out the R square values. So here we have a different value than the others. So here we can see that in decision tree regression, all the values are quite different, right? So previously we will be getting for all the 4 above regression models, we were getting a value nearby, like close to 0.60 to 0.6161, right? Here we are getting the R2 score value 0.88, which is the highest so far, right? Again we'll check for the test data now. So again for the test data it is 0.83, right? Yeah, we can see. So the values for all the R2 scores, or all the scores R2 score, RMSE, root mean squared error value, mean square error value, and the MAE is different for decision tree regression for other 4 regression models that we've used so far, right? So here again we have plotted predicted versus actual, the residual versus the predicted values, and how much predicted and the actual values are closer to the regression line, right? So next what we'll do the hyperparameter tuning for our decision tree regression, and here we can see after the hyperparameter tuning, the features importance actually came out to be, in which the temperature has the most significant importance, or the importance uh, in between all the other features, right? So yeah, so in terms of relative importance, temperature actually plays a major role. We can clearly say that, right? Next one would be the random forest regressor. So again, most of the steps will be the same. We'll be splitting the data, and we'll be getting the um, regression scores for train and the test data sets, and then we'll be getting the scores for mean square error, mean absolute error, and root mean square error, and R2 score. So again, for the random forest regressor, the values are different again. Not like the first four that we have used, like linear regression to elastic net regression. We can see the values were quite similar, but when we started using other than these four uh, regression models, the values are coming quite different, right? So here also again, for the test data also, the value is R2 sorry, R2 value is R2 score is actually 0.90, right? Next what we'll be doing is putting grid search on random forest on our random forest, and again we can see um, the data is not quite similar. Again, after applying the grid search on the random forest, the data is actually the values, actually the scores that we were getting actually got changed, right? Yeah, here we can clearly see how much the actual and the predicted values are closer to the regression line, right? So uh, we have using random forest, we will what will check is the relative importance of the features, and again the temperature has came out to be the most relative or the relevant feature. Yeah, and ours also. Yeah, so last one was, yeah, temperature and R are the most relevant features. So last model that will be using is gradient boosting, and in gradient boosting, the R2 value for the test data, the train data came out to be 0.86, RMSE came out to be 4.5308, and MSE came out to be 20.52, and MAE came out to be 3.11772. Again, for the test data, for the gradient boosting regression, MAE came out to be 3.2841, MSC came out to be 21.6810, and uh, RMSE came out to be 4.6563, and lastly the R2 score came out to be 0.8588, right? So again, what we'll do for feature relevance, the relevance of the feature, the relative importance of the features, what we'll use the grid search. We will apply the grid search on our gradient booster regressor also, and we can clearly see, yeah, the spike in the values or the changes in the values of R2 value, R2 score. Yeah. For the test data also, it got spiked up, the R2 value. So the feature importance also is the same for the gradient boosting also. When we put the grid search CV on it, so the temperature and the hour are the most relative features. So now we'll see, we can clearly see the data set in which the training set and the values we have got from the training set and the test set. Yeah. Now coming to the conclusion part, we'll start with the conclusions. So we've calculated the mean absolute error, mean squared error, root mean square error, and the R2 score for each models, and based on R2 score we will be deciding our model performances, right? And our assumption is that if the difference of R2 scores between the trained dataset and the test dataset is more than 5%, we will consider it as the overfitting, right? So for linear regression, we'll see for the test dataset and the trained dataset. See, yeah. So first of all, we'll see for the linear regression, linear lasso, ridge, and elastic, because they all have kind of similar outcomes. So from the above data frame, we can see that the linear regression, lasso regression, ridge, and elastic regression models have almost similar R2 score, which was around 61%, right? 0.61. See, 0.6160608, which was around 661 only, is around 61%, right? For the training data set and the test data set both, right? And even after using grid search CV, we've got the similar results only for these models, right? Next model we have used was the decision tree regressor, in which the decision tree regression model, in which without the hyperparameter tuning we got the R2 score of around 100%. So here clearly we can see without hyperparameter tuning it came out to be around 100%, right? For the decision tree, right? Okay, R2 score as 100% of the data set, and the test, for the test it was very less. So thus our model actually memorized the data, so it was actually an overfitted model. And after hyper parameter tuning, we got the R2 score as 88% on the training dataset and 83% on the test dataset, which was quite good for us. Next is for random forest. So before without hyper parameter tuning, the R2 score was around 98% on the training dataset and around 90% on the test dataset. So it was actually a little overfitted, right? Because the difference is more than 5%, and after hyperparameter tuning the difference is only 3%. So it is a good model for us. It will be a good model for us. Last one is gradient boosting. So before hyperparameter tuning, without hyperparameter tuning actually, the R2 score was 86% on training and 85 on test dataset. So we can clearly see that our model performed well without hyperparameter tuning, but when we've applied for hyperparameter tuning, we got the scores of 96% and 90%. So thus we've actually improved the model performance by hyperparameter tuning, and thus the gradient booster, boosting regression, and the random forest gave out with the grid CV search, actually grid search CV. Uh, they have gave good R2 scores, so we can deploy actually these two models. And as far as we are concerned with the importance of the features, for all three models, the temperature and hours played a very important role for all these three models. With this, I would say thank you so much